you know to do it. Just share the screen. All right.
So I need to temporarily.
Oh, no more. Yeah, just plug, take out the adapter for a moment.
Excuse me, Professor. Can I have a socket to plug in my laptop? This one for charger?
You can see it there.
Actually, both the sockets are used.
Okay.
Yeah.
Oh, you can see here. There are plenty of. There should be some sockets here.
Sure.
Yeah.
I will use that.
Or you can take out this one. Take out this one. It's okay. Yeah.
Oh, thank you so much.
Morning.
Okay. Is it no? Can we move the table a bit? Friend? Is it okay? Is it too close? Oh, is it? It's too close, right?
Right. Now you must feel very relaxed. Lower than here. Yeah, your score is pretty good. 95.
95.
Yeah.
Maybe she's the second.
No, she is not a second. Otherwise, I would say. Unfortunately, the competition is very high. Go ahead, you got second before.
Yeah. What was my score when I was the second?
Your score was.
I think it's 70 or 80 something.
No.
This was the Excel sheet.
It was 89 or 91.
We have only one here.
Okay, can you, if you guys need more power, just go to our lab to grab a power extension. Yeah, grab a power extension. Yeah, go to talk to Yubin. Near her desk, there's a power extension. Just grab a power extension. Keep the door open.
I loaded the sample yesterday.
Yeah, the first thing you need to do is to download the software. Oh, yeah, you do.
So what is it here? No.
That's two cluster screens.
Yeah. What's the solution for you? You can keep your laptop.
Yes, very good.
Recording in progress.
Yes, it's for me. Not for you.
So. Okay, let's now remove this. Let me remove this one. We need a, let me use this adapter. This one. Oh. All the charges here. Okay, this. These are the charges. Do you need a charger? Yeah. Okay. Can you able to connect this one basically? No. Oh, we need a. That's nice. No, no. No. You got a box of markers.
Is everyone here? Go ahead. Shall we start?
Yeah.
Yeah, okay. So thank you, Ronghui, for preparing. I mean, he spent like a few days preparing for this. Yeah, keep the door. So so I mean, you guys assume you have already downloaded the software, so you can follow Ronghui's step by step. And so we deal with semiconductors. Semiconductor deal with carriers, the electrons and holes. Electrons and holes can only interact with three things. One is electric field, right? The second is the semiconductor crystal structure itself, and the third is light. Okay, is electromagnetic wave. So in our group, we have software to deal with the three situations. To deal with electric field is axis and Silvato. Okay. To deal with semiconductor itself is DFT, bus, and quantum espresso. And third is to deal with electromagnetic wave or light is FDTD. Okay. And also actually using the console. Yeah. So but FDTD, Ronghui has used it for a long time. So when he started using it, he was not even an account. He got an offer from me, and then he accepted it. And then I told him that since you have nothing to do at that time, he was busy with the master thesis. But you can start learning FDTD. And he was a mechanical engineer at that time. He has no idea what is electromagnetic wave. He only see the visible light when he go out in the daylight. Right away. And then he learned it by himself in the spring of 2016. Okay, so 5 years ago. And then he I think every single of your papers use this, right? So,
Yeah.
so yeah, Ronghui mainly deal with electrons and carriers with light, right? But some of you don't focus only on this. Some of you deal with electric field or crystal structure. But I think eventually the trend is to when you build any device is to look at all of them. You look at it in action with light, with electric field, and with the crystal structure. So okay, so the more you learn, the better. Yeah, Ronghui, yeah, please go ahead.
Okay.
And we have a few students. So if you have any questions, stop Ronghui anytime because probably your question is relevant to all the other people too. And also for Zoomers, okay, Manoj and Wen and Glenn and others. So please, feel free to ask any question anytime because I think most of the people here are newbies, right? So most of you have little or zero experience in FTD. Most of you know what is electromagnetic wave, okay, but most of you probably do not know what is FTD simulation. So if you have any question, probably that will apply to anybody, and most of the people here. So go ahead and ask. Okay, Ronghui, yeah, go ahead.
Okay.
Sure.
Maybe somebody can take from. So firstly, I would like to say I'm truly honored to give this tutorial. The topic of today is called FDTD. Like the professor have just said, it's a very powerful tool for simulating electromagnetic waves and its interaction with dielectrics and metals. I published a lot of papers based using this technique. So I hope this tutorial will be useful for you in some way. Here's the outline of. This is the outline of today's tutorial. First, I will be touching on the basics of FDTD. Then I will talk about some specifics of Lumerical software. Then finally, we are going to do a hands-on practice. So first, the basic study in our group is optoelectronics. It's the study of the interaction of photons and electrons. There are different ways to go about this topic. One way is to do it experimentally. We grow a lot of materials and measure the properties. And then we make them into devices and measure the device performance. The other way to go about it is to do it numerically. We build a numerical model and see how the device will perform. So ultimately, the experimental verification is the final goal we want to reach. But before that, actually using numerical simulation, it's much cheaper, and it provides a lot of more physical insights into the device that we want to build. So before the actual experiments, it's a good way to run the simulations to see how the device perform. And also, by using simulation, it's easier to predict new phenomenon, and to like foresight new things. Actually, the computational electrodynamics is a whole research field which aims to develop efficient tools for the numerical simulation of Maxwell's equation and the interaction of photons with various particles. So many of you are perhaps familiar with this diagram. These are three fundamental processes we study in our group. The first one is the absorption, where we have an incoming photon and it excites the electron into a higher energy state. And the second is called the spontaneous emission, where the electrons fall down to a lower energy level and emits a photon. And the last one is the stimulated emission, where an incoming photon excites the electron at higher energy and emits, in the process, it emits two photons. This way, the photons is kind of amplified. So these are the basic process we deal with. And fortunately for us, FDTD can deal with all these three situations. So it's a very powerful way for us to predict what will happen when different structures, different optoelectronic structures interact with light. There are many different simulation tools, such as finite element method, finite integration technique, and blah, 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 a lot of other techniques. Among them, the finite difference time domain method is one of the most efficient one. So that's the reason we want to learn about it. So here's a short video about the FDTD, finite difference time domain method.
The FDTD method in introduction. The finite difference.
I want to turn up the volume a little bit.
Use the remote of the TV.
Ah.
This is the mechanical way.
Time domain FDTD method is used to solve Maxwell's equations in the time domain. The equations are solved numerically on a discrete grid in both space and time, and derivatives are handled with finite differences. It does not make any approximations or assumptions about the system, and as a result, it is highly versatile and accurate. Vector components of the electric and magnetic fields, it is a fully vectorial simulation method. Because it is a time domain method, FDTD can be.
So I want to interrupt a little bit. This is the well-known Maxwell's equation. It's the center focus of many optoelectronic studies. To solve these problems, we have a lot of differential terms, like here, the curl, and the.
I don't think that it shares screen with the Zoomer.
Is it?
They didn't share, I think.
Oh, yeah.
That's okay.
Hello, Zoomers. Can you see my screen now? Nobody's responding.
No.
No.
Brian, can you see the?
Okay, give message, it's okay.
No, they don't see it, right?
We don't know since when this problem started.
Can you guys see the screen now?
Yeah, now it is visible.
Yeah, it's on
Video.
YouTube video. Yeah. Did you miss the previous part? Do you want me to repeat it again? I think
That
we're
part,
fine. Yeah, the previous part is basically just some introductions. Nothing important. We can start from here. Okay, let's continue.
Can you close the top bar? Close the top bar.
High, lower. Yeah.
The finite difference time domain FDTD method is used to solve Maxwell's equations in the time domain. The equations are solved.
So this is the focus of many research problems. It's developed more than 100 years ago, and that's why it's so great. Still, people are still studying it. And to solve this equation, there are a lot of differential terms. Basic idea is to use many this. There's a derivative with respect to time. Then we divide the simulation into many time steps. Here there are differential terms with respect to space. Then we discretize the space into many small grids.
Solved numerically on a discrete grid in both space and time, and derivatives are handled with finite differences. It does not make any approximations or assumptions about the system, and as a result, it is highly versatile and accurate. Since it solves for all vector components of the electric and magnetic fields, it is a fully vectorial simulation method. Because it is a time domain method, FDTD can be used to calculate broadband results from a single simulation. FDTD is typically used when the feature size is on the order of the wavelength. This wavelength scale regime, where diffraction, interference, coherence, and other similar effects play a critical role, is called wave optics. When the feature sizes are much larger than the wavelength, other methods, such as ray tracing, are more efficient. A simple example where we can see the difference between wave optics and ray tracing is this triangular pattern etched in a material with a refractive index of 1.5. This type of structure is commonly used as an efficient reflective coating because light is always incident at 45 degrees to the normal, which is above the critical angle for total internal reflection, and therefore we expect the device to reflect 100% of the incident light. We can run an FDTD simulation to see what happens for two different wavelengths. In the first, the incident wavelength is 400 nanometers, or 0.4 microns, while the structure is 20 microns in pitch, or period. Since the structure is much larger than the wavelength, we typically would simulate with ray tracing. As we run the FDTD simulation, we can see the result we expect from the ray optics analysis, namely that
this is a major advantage of FDTD. We can chase the movement of the wave.
almost all of the light is reflected. The second wavelength we will use is 4 microns, and the structure has the same 20 micron pitch. Now we can see completely different behavior because there is clearly a substantial transmission, and we can even see the penetration of the evanescent field into the air. To correctly solve the second wavelength, we need a method like FDTD. FDTD is a general and versatile technique that can deal with many types of problems. It can handle arbitrarily complex geometries and makes no assumptions about, for example, the direction of light propagation. It has no approximations other than the finite size mesh and finite size time step. Therefore, it is very accurate. As a time domain method, one simulation can give broadband results. Finally, the FDTD algorithm scales well with parallelization, so it is well suited to modern multi-core and multi-processor computers, as well as high-performance computing HPC clusters. Because FDTD is so versatile, it can address a wide range of applications. These include photonic crystals, plasmonics, CMOS image sensors, nanoparticle scattering and absorption, nanopattern solar cells, OLEDs and LEDs, gratings, lithography, metamaterials, and integrated optics, to name just a few. You will notice that all of these applications involve wavelength-scaled structure.
Okay, this is a very high-end introduction on the finite different FDTD method. How do I? Oh, yeah. Next, we'll watch another video. It's a little bit deeper into the numerics of the method.
The FDTD method, solver numerics. As mentioned in the introduction, the finite difference time domain FDTD method is used to solve Maxwell's equations in the time domain. The equations are solved numerically on a discrete grid in both space and time. This means that the electric and magnetic fields, E and H respectively, are discrete in space and time. The grid step in space is generally called delta x or delta y or delta z, and in time it is called delta t. For convenience of notation, we often drop the delta x and delta t and simply refer to the spatial grid as I or j or k and the time step as n. Furthermore, we often use a subscript and superscript notation for the spatial position and time step respectively. The E fields are solved at time n plus 1/2, while the H fields are solved at time n. The derivatives in both space and time are handled with finite differences and are second-order accurate when the grid is uniform. The electric and magnetic field components are distributed in space over a unit cell called the Yi cell. This staggering of the fields in space is ideal for calculating spatial derivatives of the curl terms at the correct positions in space. At the beginning of the simulation, the E and H fields are typically 0. From here we update E at time n plus 1/2, which is a function of E at the previous time step, plus a term proportional to the curl of H at time step n. Once we have the E field updated to time n plus 1/2, we can proceed to update H at time n plus 1, which is a function of H at the previous time step, and the curl of E taken at time step n plus 1/2. In this way, we can leapfrog the update of E, then H, then E, and so on until we choose to stop the simulation. It is important to understand that we do not ever calculate E and H at the same point in time. They are offset by 1/2 time step. In fact, if you record the E field as a function of time with a monitor and plot it, the monitor will interpolate the original FDTD E fields to the same time step as H, so you may never notice this offset. Despite this issue, this leapfrog approach has the advantage of allowing us to obtain second-order accuracy in time, which means that the error between the electromagnetic fields calculated by FDTD and the correct solution scales with the time step squared. This means, for example, that if we reduce the time step by a factor of 2, our error diminishes by a factor of 4.
The simulation geometry is discretized into Yee cells, which, as mentioned previously, are the fundamental unit of the FDTD method. As mentioned before, the E and H field components are all located at different positions within the Yee cell. This allows us to calculate spatial derivatives by finite differences at the optimal spatial locations and gives us second-order accuracy in space on a uniform mesh. Still, it is important to understand that the E and H components are never known at the same spatial location, which can have consequences for many types of results which we may wish to calculate, such as energy density. By default, monitors that record these fields will automatically interpolate all field components to the corner of the Yee cell so that you can visualize and analyze your results at the same spatial location. However, this interpolation can be disabled, and this is useful for some advanced calculations, such as determining the optical absorption in a metal near a metal dielectric interface. In addition to E and H, we must also discretize the electric permittivity, epsilon. In most regions, this is very straightforward because we can assign a permittivity of either material A or material B. However, it gets much more complicated near interfaces because the interface can pass through a Yee cell at any position and orientation, and, furthermore, each electric field component is in a different spatial location. As a result, we need a different value for the X, Y, and Z components of the permittivity, even if all materials are isotropic. Once we have discretized the permittivity in this manner, there are still challenges. First, the position of the interfaces is not well defined within the Yee cell. For example, if we have a Yee cell with a spatial grid of 40 nanometers and we move an interface by as much as 20 nanometers, we may not see any difference in the FDTD results because the permittivity discretization could be identical. Second, we do not treat the normal E field components, which are discontinuous, any differently than the tangential ones, which are continuous. Third, we can experience staircasing effects when interfaces are on an angle with respect to the Cartesian axes, which can lead to problems such as unphysical hotspots in plasmonic devices. The conformal mesh technology is a method to deal with these issues by modifying the standard FDTD update near interfaces to use an integral solution to Maxwell's equations. This is equivalent to introducing an effective permittivity that is anisotropic and can provide a much more accurate solution. We will discuss the conformal mesh technology in more detail later. FDTD simulations can be run in 3D or in 2D. It is important to remember that for 2D simulations, the structure is infinite in the Z dimension. In some cases, 2D simulations are an approximation that can be run quickly, but in other cases they can be a fully accurate solution to the problem. For example, simulating line gratings, like the one shown here on the right, illuminated by plane waves, should be done in 2D. Because 2D FDTD simulations make the assumption that the structure is infinite in the Z dimension, we know that the permittivity and fields are the same for all values of Z. This allows us to separate Maxwell's equations into two independent polarization states, often called transverse electric, or TE, with fields EX, EY, and HZ, and transverse magnetic, or TM, with fields EZ, HX, and HY. In FDTD solutions, we try to avoid the terms TE and TM because they can lead to a great deal of confusion. Instead, it is best to look at the blue arrows of sources in the FDTD design environment to see the direction of E-field polarization. In certain cases, such as anisotropic materials with off-diagonal elements, this separation of polarizations is no longer valid. In general, you simply set your desired source polarization and, in 2D, FDTD solutions will run a TE, TM, or combined TE and TM simulation as required. It is important to think about how the memory and simulation time scale with the grid size. If we assume that the spatial grid size is uniform and that delta x is the same as delta y and delta z, then the memory requirements for 3D scale like 1 over delta x cubed in 3D and 1 over delta x squared in 2D. This is obviously expected, but what is surprising is that the simulation time increases, like 1 over delta x to the 4th power in 3D and to the 3rd power in 2D. The reason for this, which we will discuss in more detail later, is that you cannot reduce the spatial grid size without also reducing the size of the time step, delta t. This means that there is a big penalty to pay for using a smaller grid step. For example, if you reduce your grid size by a factor of 2, your simulation time will increase by a factor of 16. Also, we often discuss the grid size not in absolute terms, but relative to the wavelength of light. We call the ratio of the wavelength, lambda, to the grid size, delta x, the number of grid points per wavelength, or sometimes just the points per wavelength. This is a key factor that determines the accuracy of the FDTD simulation. As a coarse rule of thumb, you can get initial FDTD results with 6 points per wavelength, and many results such as transmission and reflection will be within 10 or 20% of the correct answer.
Does it mean the simulation time and memory requirement is only depend on spatial grid size?
Yeah, exactly. Depends on how many grids you have. The more you have, the
In the space only.
Huh?
In the space only.
in
Space
space.
means not time.
Also in time.
So
You can define the time step size as well, but usually that's dependent on the speed. Once you discretize the space,
yeah.
the time the step time is dependent on the speed of light, so it's fixed. Yeah. So it's only the
only independent variable is delta x.
yeah. Here this value is very important. It's like an empirical value to get good first results. To get this dx. This is the spatial grid size equals to lambda divided by 10. This is like a rule of thumb when you want to do calculation. The grid size should be the minimum grid size should be this value.
10 points per wavelength, many results will be within 1 to 2% of the correct result, and it is rare to require more than 20 points per wavelength. I should note that this is a rule of thumb only, and sometimes much smaller meshes are required to resolve geometric features or to correctly simulate plasmonic effects where high light confinement can occur. It is also important to note that the points per wavelength should be defined with respect to the wavelength in the medium and not the free space wavelength. Therefore, for similar accuracy, a smaller grid size should be used in materials with higher refractive index. Lumerical's FDTD solutions provides a simple mesh accuracy setting that targets a minimum points per wavelength in all regions of the simulation and automatically adapts to the refractive index of the different materials. The mesh accuracy of 1 through 8 corresponds to points per wavelength targets of 6, 10, 14, 18, and so on up to 34. The default value is 2, and this is appropriate for most simulations. Initially, you may want to even use a setting of 1 until everything else is set up properly. It is rarely useful to use values of larger than 3 or 4, as there is typically something else that limits the accuracy of the simulation at that point. For fine geometric structures, or situations such as plasmonic structures, where you know the light confinement will be high, the mesh can be controlled locally using mesh override regions. In the two figures on the lower right-hand side, you can see some results of convergence testing for a 3D CMOS image sensor application. The first figure shows the fraction of source light that is incident on the silicon surface and the fraction incident under the green pixel as a function of mesh accuracy. You can see that good results can be obtained with a mesh accuracy setting of 1, that by 2 you have almost achieved a converged result, and that there is no point in going beyond a setting of 4. In the second figure, you can see the cost in time and memory of the higher mesh accuracy setting normalized to a mesh accuracy setting of 1. you can see that it takes almost 600 times longer to run with a mesh accuracy setting of 8 compared to 1. In this application, where a mesh accuracy setting of 1 can run on a single workstation in a minute or less, this can be the difference between waiting 1 minute and waiting 10 hours for your simulation to complete. Yet the results are almost identical. Clearly, you want to be working where each simulation takes only 1 minute, which makes it easy to perform complex parameter sweeps and optimization.
Okay, this is the introduction on some of the numerical schemes used in the software. Go to the next page. Next is an introductory video on the software that we are going to use. It's called the Lumerical FDTD. It's a very short video that introduces some of the main features of the software. The LEDs and photo detectors are a main topic in our group. So this software can be used for that as well. Okay. So those are all the background knowledge I want to cover. Next, let's take a look at the software. I think all of you already have the software installed, right?
Yeah.
Okay. So let's open it. Share screen. So this is the software on my computer. I think it might look a little bit different on yours because the one you installed is a much later version. Mine is the 2019 version. I think yours is the 2021 version.
Can you close the top bar?
Might floating. It's this originally the company is called Lumerical, but it has been acquired by ANSYS, I think in last year. That's why now the software is called ANSYS FDTD, yeah, or something. We double click to launch the application. On my software, this is what it looks like. I think it looks a little bit different on your computer, but the main idea is the same. I go to the products bar, menu bar, the one on the top, the first one, products. Then here at the top, there's a entry called FDTD 3D electromagnetic simulation. Here, I click on new project, and the FDTD will be launched.
Ours are totally different.
Yeah,
We
because
don't see any
we have this like
product.
inside the solver. Inside the solver.
solver.
Solver. Yeah.
Oh, that means if you some of it, if you see a screen asking you to
It's the third option, right, for Jose?
yeah. If you see
Jose, can you sit next to Ronghui? Yeah, so that he know what is the latest interface.
I think you have to activate the license.
Yeah.
On a model and restart the system. I think so.
yes.
Okay, so request an evaluation?
Yeah,
And this is the initialization.
log in. If you are on the screen asking you to input a license, you go to the third option to request a trial license. Yeah, double click. Open. The third one, third option.
Okay, sure.
You want to? Request an evaluation license. Have you registered an account yet?
Yes. I do this.
Everyone will get 10 points.
Oh, you're sharing it. You? Oh, yeah. Seems like you are the.
No.
You're the only ones.
Mentioned this login, correct?
Succeeded.
This one?
Yeah, yes. No license.
You can join through Zoom. Oh.
Communicating. There should be like a license here. You just need to
Use a
activate.
message to them. I also message.
Hey, Scotty, do you know how to do it?
For this one.
Yeah, can you come and
Sure.
Yeah.
Oh, yeah. Now you have it installed.
Let's not log out anything. let's just minimize it. Restart it and open the software itself. I mean, restart the whole system itself. Even yesterday, I was facing the same problem, but after restarting, it was totally working. No, I mean, laptop itself, you have to switch it off and turn it on.
You need to restart the
Restart the
laptop?
system, yeah.
Oh,
Restart.
yeah, maybe we can share that. Restart the
Computer.
But it was logged successful.
Yeah.
Okay, so after that, what we will do, you have to go to the any example, it will ask you to start the trial version. So and then it will activate the key after restarting. Okay.
Why it's so complicated? When I tried this, when I tried to get a Thai license 3 years ago, it was much easier.
Much more easier. Right?
I just need to send an email to the company, and they will give me a long number, and I can use it directly.
Because that's manual. That's too slow. No, it's
But
automatic.
this is even slower. You need to.
It's slower on the user side, so the company has their money.
So I open it.
The previous way is a longer time for the company.
From companies, they made it automatic.
Yeah. Yeah.
Yes.
No.
Yeah, it's currently. Yes, yes, I got. Now you can try to open the software.
Anybody else have the same problem?
Is it correct?
Yeah, it's login, right? After if you click the login, it will go to the website. Yeah, login there, automatically it's the registration going inside. No, I mean the software itself initiate the process. Okay. Yeah.
Is it normal to take so long for you to login?
Maybe you have to. Can we able to go back and start it again? And software, let's go back. And then you click it. Sure. Is it open? Can you right click and then run as administrator? That's open. Yeah.
Is it because your computer is slow? It's a gaming computer.
Yes, yeah, login. Okay. It's taking more time. Oh, wait. Yeah. Yeah, click this one. Do this. It's like reach the go. To have gallery. It will. Photo solvers. Go to the person. Go to the first one. Double click. Can you please remove everything? Yeah, okay. Make the first one.
Yeah, evaluate.
Evaluate first, yeah, yeah. Okay, sign in, okay. Request. Okay. They will need to contact sales.
I tried yesterday, but
Yeah, I also feel like several times.
Did you also face the same issues?
And let me, so, following that,
No.
go back, 3 steps, right?
Yes. Go.
Next,
Yeah. Did you go to the app gallery before?
yeah. Sample
Solvers.
solvers.
Evaluate.
No, the first one, right?
Yeah. Same issue. Let's see. Because yesterday I was able to activate the license for the specific thing. Request when user have already tried what are more.
No,
of the
not
process.
license, solvers. Evaluate. Sign.
But also you can go up to.
Figures, how did you do it? Can you tell them about other students? Do you have any trick to help them?
I think.
How come they couldn't do it?
I think all the rest have already installed. Only Jose and Nan.
Because they sit nearest me.
Electromagnetic energy.
I know.
So which step are you on? Should be working. Right?
Did you create an account on the website?
Yeah.
Oh, did you
Receive
you need to get an email and
We are facing the same issues.
tried yesterday, but
No contact sales.
It says that you have already tried.
I tried it
For other
many
products.
times yesterday.
Request trial license.
yeah, request.
But it should be for 1 month. But after this request, it was downloading and it was activating the process. Can we log out and log in again?
I think okay.
Maybe.
Yeah.
Now
you're good to go.
Okay.
Account with
After
another email ID.
it will restart the software.
And then evaluate for.
Okay, I think let's see.
Okay.
Yeah.
That also. So.
No, come on.
Do you have another?
Okay, so now just
So you can you try to log out and log in and activate the event?
Yeah,
sign up with email ID.
sorry. Log out, enter to that, log out,
And we can log out.
and after log out, sync in with Lumerical, with the one. I use your email as the register and
Did you solve the issue?
yeah, I saw using say
With the numerical.
yeah.
Okay. So then did we sign in through ANSYS then before? That's why it's.
Yeah, could be. Yeah.
So okay. Let's start now, right? So,
Yeah, we have to restart one step is the question.
And then
A
try
solver.
this.
okay, now like this.
Yeah.
New project, right? Yeah.
What is this? No.
In that case, I think you can connect to our floating license.
Yeah. This should upload. Restart now.
You go first. Don't cancel.
Okay, let's see.
Is it working?
Try this.
Have you tried what they suggested? Log out first, then log in, use the.
Check software if you are not ready to do it.
Sign up with other Miller.
Then open that. I mean,
It's also Honor.
Yeah.
Mine is also Honor only.
Does the floating license work?
No.
Wasn't there a window before
Honor
behind
X
this
one.
one?
How about yours?
7.
Is it X7 or 7?
7.
7. Okay.
7, 8.
This is 5 years old.
This is only 2.
But how many years?
2 years. In my first year, I was because I thought, I think so.
Next year you can see Apple.
I will not buy it because in Toyota there is much more other expenses. So you have to be take the iPhone also. Charger is not cheap. Otherwise, should buy.
No, I didn't receive invitations in the electronic invitation. Okay, let me check the. No. Okay, yeah, that's good because already people are there. Waiting for you. But it's not there in the list. Won't take it. Who sent this one? You will. Can you reply to that mail and tell that I'm waiting for the Can you also click cost email also? No, let it be Gmail. I'm also link that please email it to me and I will distribute it.
You can your computer.
Seems like for us, for the electrical installation, we have one more slot, right?
Tomorrow?
I mean,
I don't know who's.
okay, you will someone handling. Seems like we have one more slot today.
Today actually. Yeah, so who decided to attend?
I'm interested to attend, but my email address is not there in the list.
Okay.
So
There's Dano, there's you. You. I think that's all they do.
okay,
I think only good. I think maybe one. I think yeah, that's the only people that decided to attend.
Yeah, why don't you guys take a 5 minutes break? You know, get some water, go to the bathroom, and then come back. Good, how are you? Fine.
Tomorrow we have one to one.
Yeah. You ready? Yeah, it should be okay.
Okay. Yes, I don't know, so.
Right. Yeah, I tell you.
Okay.
Now for the tier. Did you solve this? What's the problem? But
The request, we generate the request, but the license is not yet ready.
Yeah.
是不是不能这个声呢？因为我不是说我听到。你试试我那个到时候可以不是我不知道是不可以。这个。
Doesn't work.
It's okay. I mean, she can just sit next to another student or.
Okay.
Mine really works.
Yeah.
They want to go take a look?
Yeah. Why not? Coffee time. Oh wow. It's already from covalent bond. Kalam, do you guys have problem? That's good. Is you okay?
My key is it connected already?
Sorry.
Why is that? They don't like you?
Very much.
or the.
Where's everybody?
No, you have to press the escape. Yeah.
Ah.
Sure. It's okay. It's just yeah. Glenn and other people, do you have problem?
No, I already have it, like in the screen, shared screen.
Good. Danu, how come you're not here?
Professor, I will be joining through this because I took NAS computer. I can't install, so I installed here.
Oh, okay.
Yeah, last time.
Yeah, now you can sit next to another student. To you know. Jiga, would you like to sit next to her and you know, you can share your computer together? Like, just grab your chair. You like, yes. So there's another one you can use. You can sit next to her, so you can share the same computer.
So. Yes.
Ronghui, you don't drink too much coffee, right? Maybe you should stop drinking tea.
Yeah.
Why does Ronghui have to drink more coffee?
No, he's saying, I'm just asking him, I remember the last time he was saying he doesn't like to drink too much coffee.
Oh, okay.
Yeah, so I'm saying tea is a good alternative.
Is everybody here?
I think it's only saying Shah. No, Shah.
Shah. We shall light it.
Hi, Glenn. When you come into house?
Well, I haven't received the ticket yet, but the relocation team told me that I'll be in Saudi 8th of June. But as I'm not vaccinated, I will have to spend 7 days in quarantine, and after that, I'll arrive to CAF.
Do you have US visa?
Yeah.
You can go to the US, take the Johnson & Johnson vaccine one shot, and then come to Saudi Arabia.
Yeah, but the problem with that is, I think if I go to USA to take the vaccine, I will have to wait other 14 days because there's some regulation you have to wait. There are some countries, like I think USA is among them, that if you were there 14 days before, you have to wait.
What do you say?
He used to wait. But Glenn, if I remember, they just sent an email recently about the United States is not banned anymore.
Yeah, the US is not banned anymore. So you can, like I said, you can go to the US, take the Johnson & Johnson vaccine, just one shot, and come to Saudi Arabia, no quarantine.
Okay, I'll check that.
Yeah, I mean, US was on the list. Now US, UAE, they are not on the list.
Oh, okay.
So you go to US, take the Johnson & Johnson, just one shot. After that, you come to Saudi Arabia, and you just have to stay at home for a few days. That's it. You don't have to go to the hotel.
Okay.
Okay, let's continue. Yeah. Okay.
Okay.
Yeah. Glenn has no problem with this software.
Okay. So now that everybody has installed the software, we can go on and take a look at it. So at this main launcher, we go to the top menu, products, and then here FDTD 3D electromagnetic simulator. We open a new project. This is how the interface looks like. So is everybody on the same interface?
Yeah.
Okay. So this is the main interface. We can adjust the window size a little bit. The full black window, this is the main graphics window. So all your structures, all your monitors, your whole simulation area is displayed in these 4 windows. We can see here XY view, XZ view. This is the perspective view and the YZ view. These are your simulation area viewed from different perspectives. Here on top, these are the standard Windows menu. We have File, we have Edit, we have some other menus to do global settings for the software, such as the default layout, the default units, and other things. Below that, we have a lot of icons. Here, the first one is the materials. This is where you define your simulation material, such as silicon or gold or any other user-defined material. It looks like this. You can click on it, and it will open this material database window. So here we can see a lot of built-in material. It's sorted in alphabetic order. It starts with the silver because it's AG, and then it goes all the way to W, tungsten. We can, so as the simulation goes on, we can select materials from this menu. We will close it for now. The second icon is the structures. So here, if you click on the main icon, directly it will create this rectangle. But if you click on this inverted triangle, we can see the many more structures came out. There's triangle, there's rectangle, there's polygon, circle, all kinds of different shapes. This can be opened by this inverted triangle here. This is where you define the shape, shape of your structures. For example, if you want to simulate a rectangular LED, the first thing you need to do is to create a rectangle from it. And the third icon is called attributes. This is used for some more advanced transformation. To be honest, I never use it. This next to it is the components. Also, by clicking on the inverted triangle here, you can see a lot of built-in optical components, like this extruded polygon is for complicated polygonal shape, and grating, integrated optics, and photonic crystals, surfaces. These are all pre-built photonic structures. And next to it is called groups. Here is where you group many of the objects together. Here there's this one container is where you group many geometrical shapes together. For example, if you created 100 rectangles and you want them to form a group, you use this function. This structure is slightly higher. Apart from the structures, you can also use code to generate the structures, and the generated structures form a group automatically. And this analysis group is even a step higher. Apart from using the code to generate structures, you can also use code to generate some post-processing function to it. So each one is a bit higher than the previous one. Next to this groups icon is the simulation icon. Same thing. You click the inverted triangle. There are two options. The first is the region. This is where you define your simulation region. For example, if you want to simulate an area of 10 micrometer by 10 micrometer, then you define a region here of 10 by 10. The second one is the mesh. Just like we introduced earlier, the FDTD is based on discretizing the structures into meshes. So here, this mesh function is for us to discretize the structure. And next to it is the analysis function. Here, these are all built-in analysis functions, post-processing for the far field, for the optical power, for Q factor of the resonators. We will be using this analysis group later. And next to it is the import. This is where you import from other file formats. You can import a GDS file, and you can import STL file. These two file formats are used to define complicated shapes. For example, you can simulate a 3D panda shape or 3D dog shape. These can be imported from here.
What's the image? If we import the image, what can that do?
To be honest, I never use it. I don't know. Maybe just an image as a reference. Then later you can draw on it. This build, I never use it. No idea what it does. So, I think this one, if you have a structure with different layers, stacking of many layers, you can use this layer builder. But usually I just use command to do that. It's much easier. This is an important one. It's called sources. Again, we click on the inverted triangle. There are a wide variety of different sources. We have dipole source. It's a point, and we have a Gaussian source. It can be used to represent a laser beam, and we have a plane wave. This is the most fundamental source. This total field, scattered field source is a special source we will be using it today. And mode source is used to excite the fundamental modes of photonic waveguide. And next to it is also another important one. Important one is monitors. And so this monitors is used to collect results. For example, the electric field distribution and the magnetic field distribution. And there are many forms. You can either collect the time domain information, how it evolves with time. You can also create a movie of the how the field evolves. You can also collect the data in frequency domain. These two. You can also get the mode profile. Finally, this global properties is used to define the global properties of these monitors. These four, 1, 2, 3, 4, we don't use it so often. So I will skip. They are not that important as well. Among them, these resources is used to check how many simulation servers do you have. It's used. It's mostly useful for like when you have a cluster. Finally, the check. This can be very handy sometimes to check the. If you go to the second option to check the simulation and memory requirements. If you have a very big model, you are not sure whether your computer can handle it, you can check using this function first. Finally, this is the ROM menu. You click it and the simulation starts to run. So this is the main toolbar. This toolbar is the most important. Will be all our simulation will be defined by using this toolbar. And then here on the left-hand side, we have a few tools for editing and for viewing. For example, this one is to duplicate a structure. We already have a rectangle here. We click this duplicate. Now it becomes two rectangle. See? Here there are also move, array, and delete. We can also delete this one. These are some viewing options. In particular, this magnifying icon is it's very handy sometimes. When you click it, the selected object is zoomed in into the is zoomed in. Next, I want to introduce the operations into the operations of this viewing window. First, let's create a structure here. I already did this one. We go to structures and click circle maybe. Then a circle is created on the main window, right? The middle wheel, the middle mouse wheel is used for zoom in and out.
Or we can move the object.
Move the object.
Click it and just grab it.
Yeah, click and grab it.
Just like symbol. Just like remove and table and click in the center. See that? Actually, I need to select. Oh, this one. No. This is the same.
So we can move it around and zoom in and zoom out. Sometimes if you zoom, if you like zoom out too much, your structure totally disappeared. Here is when this icon comes in very handy. Zoom extend. You click the zoom extend, everything is back to normal. So this is I want to share. Next, this area is very important. It's called object tree here. This object tree, all our models are defined here. It's, for example, if you have a source, you have a monitor, you have a structure, they will all be displayed in this area. It's our main working area here. And on the right-hand side, we can see this script file editor. This is where you write the scripts. So you can write some computer scripts and run the scripts for automation purposes. For example, if you want to build a thousand cylinders, then this is very, very helpful. You cannot do them one by one. It's you have to do it by using a scripting language. This is where we can do it. So the new script, open script, save, and finally this is the run. Yeah, this is for running. And below this script window is the object library. We can adjust the size a little bit. For any menu, you can click on the boundary to adjust its size. So here, object library, there are many pre-built objects. This includes Complicated geometrical shapes.
I can't find this one.
Somehow, if you cannot find this, if your interface looks a little bit different from mine, you can click here, go to setting. Oh, view.
It's different.
You can go here, view, set default layout, and then choose default layout. Then everything will look exactly the same.
No.
Huh? Still no?
View Windows.
Default layout. If that doesn't work, then go to the next one, view Windows, and open everything. Right side.
But the question is not coming here.
Yeah, do your own hands-on. If you have any questions, just ask Ronghui. Okay. He will only do this one time in his life. So no more second chance. Well, my office became a superconductor computer with so many CPUs running.
What?
Let me check.
Oh my God. I think they're choosing this for some purpose. But maybe then I choose the other one then. Interesting.
Yes, now
Maybe restart.
this window on that side, is that's
Now you have it. Set default layout. This usually will bring us to this this window. So we were talking about the object library here on the right hand side. Here there are a lot of pre-built objects. We will come to that. We will come to that later. You can select any one of them. For example, grating. If you want, I want to build a grating. Select it. Then if you scroll down, there's a insert. There's a insert menu where you can insert it. But yeah, again, see, it's a little bit out of proportion. We can click this zoom bar to like make it in proportion. So this is a very useful tool. We will come to that later. So this is the interface introduction. Anybody having any problem?
so if we want to make another object like Cyrus made, then if our object which we want is not available in libraries, then how can I make new one?
It's a very rich library actually. You can create almost all the shapes.
I think we have to take different dimension and we can merge it.
Yeah. If it's not available here, you can always write a code like to divide your geometry into pixels. So you add a lot of rectangles, And just like what you do with for example, if you for each pixel you add a rectangle, then all the rectangles can form like any shape you want. That's usually what I do.
Okay. So we have to define those pixels through program.
Yeah.
Okay.
Yeah.
So how you write a script to create more, like for instance, you talked about earlier. So can you write one script so
we have a reference.
I can show you how to.
Okay, it's a function.
Yeah. So you
Interesting.
you can use this code here.
Oh.
And then
Here I delete it first. Oh, I haven't saved the file yet.
Okay.
Again, click this zoom. Yeah. Now the geometry is created. This I use this script. It's very powerful. If you want to add 1,000.
Oh, I see. It's like a C.
Yeah, you can create a loop.
Okay.
Different locations. Maybe that's
Times, maybe plus.
Then it will create. This will create an array of rectangles shifted in the x direction. Let's see. Yeah. Maybe that's. First, let's delete everything. Yeah. The
five.
Yeah,
Stuck it
an
in
array
the
of yes.
Script is easy.
Yeah. I do a lot of things in the script. That's why a lot of these like stacks, and then we use it.
Okay.
Here, this is the on the object tree is all the geometries and all the monitors, all the sources you have defined. You can choose them. You can select them first. You by your left mouse button, and then right click. Then you can do all kinds of operations. Delete. Yeah. Now it's going in another direction. For example, if you want a complicated shape, you can use these rectangles to build them.
Oh.
To like a sort of assemble.
Okay, it's going X and then Y.
Yeah.
Okay.
It's just a simple demonstration.
Yes, you have to just play with this stuff.
Yes.
Okay.
Sure. You can make the remains.
Any more questions?
Let's make the first most complicated script to understand.
This is a more advanced function. Yeah. This is just a demonstration. In order to run the scripts, you need to put more effort. Yeah.
Address is just for only for a time.
Yes.
Multiple structures has their own commands.
If you want to name new
set. The new rectangle name is
circle. Yeah. Okay.
We can also
add circle.
Yeah, add circle.
If you want to add, then
the circle, the name will be saved as new rectangle because we didn't change the name.
Oh, there's a mistake.
Okay.
Because the circles are not defined by the x and y dimension, it should be defined by the radius. So for add circle, we need another set of commands.
It's like the MATLAB. You have to go and check the commands. And
Yes.
Do we have these directories directly in the software?
Huh?
Do we have all these commands directories in the software instead of going to internet?
You can. I don't think so. You can, but here the documents. Maybe you can check here.
Okay.
Yeah.
Sure.
There's no manual for this software, but you can. There's a large number of
documents.
Yeah, websites you can go to browse.
Sure.
So these are more advanced functions. I will not cover it today. In order to learn the scripting language, you need to put much more effort.
Sure.
You need to use it from time to time. So this is the interface. Next, we are going to use this program to solve a specific problem. It's called the Mie scattering problem. Let me open the.
Excuse me.
Yes.
It's not shared to them.
So what is the unit of this? For example, it says radius equal to 5 minus 6. So the default unit is in, yeah.
It's the default unit is meter.
Oh, okay. Thank you.
Change that, though. You can choose.
Yeah, I think you can change the default from here.
But no, it's in microns.
So.
But in scripting, it's always meter. In scripting, the unit is always meter.
Oh, okay.
Yeah. Here, the setting is only for the graphical interface.
Okay. User interface.
Yeah.
Okay. Oh, actually, it does say when you have a unit, it will. If you create a structure, and then you click on it, it will show you the units for the size. If you create a structure instead of by defining the code, click on the structure, anything, and you right click on the object properties. Edit object.
Edit object.
Edit, yeah. It says micron.
Yeah.
It's in microns.
Yes.
Okay. Yeah, so you will know basically.
Yeah, exactly.
So we can also reconfirm it.
Any more questions? If no, then let's look at a specific problem. Let me share my
Just
screen.
open the Mie scattering. No, you sent us. Should we open the one you sent us?
No need. Let's go through some background knowledge first.
Okay.
That one is already made model. Yeah. We are going to go start from scratch.
Close the top part. Yeah, thank you for preparing the background knowledge.
So no problem. So this is the problem that we are going to tackle today. We have a dielectric cylinder, and incoming wave impinges on the cylinder, and the problem is, what's the distribution of the scattered field? Obviously, when this incoming wave impinges on the cylinder, it will be scattered in all directions. And what we are interested in is what's the intensity of the scattered field at each direction. So for this circular cylinder, there's an analytical solution, and it's defined by this bunch of equations. You can see it's very complicated, but it's only for circular structures. If we have slightly deformed, like an ellipse, then this solution will fail. That's when the numerical solution comes in very handy. So here's our simulation strategy for because you are using very weak desktop computers, so we will be working in 2D. And also to save time,
Can you explain why, like, in what situation 3D is definitely necessary, and in what situation 2D is acceptable?
In our case, we are simulating a very long, long cylinder. We can assume it extends infinitely into the third dimension. In this way, we can assume this is a 2D simulation.
So how about 3D? In what situation?
For 3D, if the cylinder has a finite thickness, finite length, and the length is comparable to the wavelength, we definitely need to simulate in 3D.
For example, 500 nanometer.
Yeah.
If it's 500 nanometer long, then 3D is necessary. But if it's like that, 5 micrometer, which is 10 times larger than wavelength.
Yeah, then we can neglect the third dimension.
So if it's like at least 5 to 10 times longer than wavelengths, you can just assume that you can use 2D. But if it's comparable, because the point of using FDTD is that only when wavelengths are comparable to the object of interest, then you use FDTD, right?
Yeah.
Then if your object is much, much bigger than the wavelength, okay, there's no need to use it. Then you can use the so-called ray tracing. Okay, so you just assume the light just trace like a straight line and then it bounce, just following just the very basic physics in terms of refraction and others.
Yeah.
So in Ronghui's research, sorry, one more thing is that most of his structure have comparable size as the wavelength.
Okay. Which wavelength you are using? Which wavelength?
Visible and UV.
Visible, like a few hundred nanometer. He never deal with structure that has 10 micrometers. Yeah. So most of the structure he has dealt with a few hundred nanometer. That's why he used FDTD. Okay. So FDTD does not work in every single scenario. It only works when they're comparable to it.
Yeah. Also, the beauty of the nanostructures is that they interact with the light more strongly than those big structures. So let's go back to the main topic. So we will work in 2D, and we will launch a plane wave towards the structure, and we use the new FDTD to propagate the field so that the scattered field and the direct transmission can be calculated. And this scattered field is actually equals to the total field divided by the direct transmission. For that purpose, we have a special kind of source to do that. It's called total field scattered field source, TFSF source. As the name suggests, this is a special source used to specifically deal with this kind of problem. It can to calculate the scattered field of nanostructures.
What's the difference in plane wave source?
The plane wave source just launch a plane wave toward the structure, and it doesn't care about what happened next. But for this source, it can subtract this direct transmission for you, and what you get is only the scattered field. Here I have a video to explain this TSF source in detail.
The total field scattered field, or TFSF source, injects a plane wave with finite span and separates the computation region into two regions. Inside the source region, both incident and scattered fields are present.
We can see in this cartoon, there's an area defined here. Outside of that area is a purely scattered field, but inside this area is a mixture of, it's more clear here. Inside this area, is the incident field plus the scattered field. It's much more stronger. But outside this field, we can see there's a discontinuity at the interface. See, right? So outside this boundary is the scattered field.
Where does this flux come from? It's part of the source.
Yeah, it's part of the source. We need to define the size of this box.
And outside, only scattered fields are present. The total field scattered field source works by subtracting at its boundaries any light which is directly transmitted through the source region or reflected from a flat substrate, so that only light that is scattered by a feature contained completely inside the source region will pass through the boundaries and propagate outside to the scattered field region. To get a better idea of how the source works, it's useful to consider what happens in the simple case when the source is injected in free space with no scattering objects, as shown in this movie. The plane wave is injected from one side of the source region and subtracted at the other side. Since there is no scattering, the fields are 0 outside of the source boundaries. When there is a substrate, any light which is directly reflected or transmitted through the substrate gets subtracted at the boundaries. The source is able to determine what portion of the fields correspond to directly transmitted and reflected light by using one edge of the source as a reference edge, illustrated by the yellow line in the image here. The refractive index profile of the structure along this edge is measured, and the fields that would be directly reflected or transmitted by the reference refractive index profile can be calculated. This is what gets subtracted at the boundaries during the simulation. Since the refractive index profile at the reference edge is important for this calculation, the side edges of the source should always pass through the substrate and not intersect with the scattering particle. Since the total field scattered field source injects a plane wave over a finite span, the default normalization method, where the transmission result from the monitors is normalized by the amount of power injected by the source, leads to arbitrary values. Because the power injected by the source depends on the size of the plane wave injected in the total field region of the source, it's usually more physically meaningful to normalize transmission results by the source intensity, and this is also known as cross-section units.
So I guess most of you have heard the scattering cross-section and absorption cross-section. It's the total scattered or absorbed power normalized by the size of the particle.
Section units are usually used in Mie scattering simulations to get the absorption, scattering, and extinction cross-sections. There's a discussion about the different possible normalization methods when using the total field scattered field source, linked below. The total field scattered field source works with absorbing materials and anisotropic materials, and it works with multi-layered substrates. It can also be used to simulate standalone scattering objects or periodic structures in conjunction with periodic or block periodic boundary conditions. Here are some examples to illustrate some of the rules for setting up total field scattered field sources. If using PML boundaries at the sides to simulate a single standalone scatterer, the source should not extend into the PML boundaries at the sides. If simulating a periodic structure, the source can extend through periodic boundaries. If there is a substrate, the source injection axis should be perpendicular to the substrate. If there is a substrate, the edges of the source should intersect with the substrate. The source should not intersect with the scattering object. Some applications which use the total field scattered field source are Mie scattering and defect detection.
We will be building exactly the same model today. It looks like this. Here, the green line, green rectangular line is the source, and these yellow lines are some of the monitors to monitor the field intensity and to calculate the cross section.
total field scattered field source is useful when you want to be able to separate the scattered fields from the total fields and perform analysis on the scattered fields only, such as by getting the scattering cross-section or the angular distribution of scattered light in the far field. In the next unit, we'll set up a total field scattered field source to measure the scattered fields from a particle which represents a defect on a structure.
Okay, so that's some basic knowledge about this source we'll be using. Next, let's do the hands-on practice. We are going to build this mean scattering model. We will calculate the scattering cross-section of circular objects.
So are we going to make it from scratch, or are we going to?
Yeah, we are going to make it from scratch.
A new project.
Yeah. Firstly, I would suggest you to restart the program so that you get a clean interface. Is everyone ready?
Yep.
Okay. So the first thing we need to do is to build the circular shaped circular cylinder. To build a cylinder. The way we're gonna do that is to go to the structures and click this inverted icon, inverted triangle icon, and click circle. Then a circle will be inserted into the at this interface, and then on the circle we click here at the objects tree. We select the circle and right click, edit objects. This window defines all the properties of the circle. First, the name. When we want to give it a name, we will keep the default. And this geometry tab defines the geometry. X, Y, this is the center. We will keep it 0, 0. And this D is the center of the Z direction. Z span is the height of the cylinder. We will put 8 here. And this radius is the radius of cylinder. We put 2 here. Next, we go to material. This will define the material of the cylinder. For now, we will keep the material as object defined dielectric. We only change the index 1.02.
Right. I mean, there's a lot of them will do simulation related to dielectric materials such as gallium nitride and oxide, this kind of stuff. How do they customize the index?
Maybe later I will show them. This is like a basic training. So
okay.
Also, we want to verify the results, so I use this fixed index here.
Why does the index have units of microns? It shouldn't. Should have no units.
Yeah. I have no idea what this what this does. So its index is like a unitless value. So we can neglect this. I think it's related to the.
Maybe it will scale it.
No. If you put a function here, maybe that's the index of your like wavelength. So the rotations, we can leave it alone, and this graphical rendering, we can also leave it alone. The index 1.02, everybody got that?
Yeah.
Okay, then we click OK. And we can see
Why did you choose 1.02? That's good.
Because I have already an analytical solution to compare against. So
okay. The 102 is just barely above 8.
Yeah. We can notice that it becomes very large. Then we can click this magnifying icon to zoom it, and now the display is normal. After this circle has been defined, we will next define our simulation region. So we need a box to define to tell the software which part of what's our simulation area. So it's here. We go to simulation and click this inverted triangle and select region. After we do that, we can see a yellow box appear on the screen. And then we go to this objects tree, right click, edit object. Same, we need to do some settings. The first thing we need to do is on the general tab, this dimension, we need to set to 2D. Then
yes, different.
Huh?
We have it slightly
different.
Oh yes.
It has the same
background and access.
We do have the same, but it's arranged in a different way.
Yeah. Anyway, here we only need to change the dimension to 2D.
Yes.
And next we go to the geometry tab. This will define the size of the whole simulation area. For that, we the x center 0 and x spine 7, y center 0, y spine 7, c 0, like this. So this will define a 7x7 simulation area. Yeah. Remember to set the center to 0. Oh, sorry. Here I made a mistake.
I was going to ask you.
The center should be 0.
So it's centered at the origin and would span 7 everywhere.
7 to the x and 7 to the y.
Yeah. Next, we're going to go to this mesh setting. This defines the mesh size.
How many mesh?
Yeah. The mesh type, we keep it auto non-uniform. So FDTD has this, Lumerical has this algorithm to generate automatic meshes. We can use it. So here we only need to set the mesh accuracy. Let's set it at 5.
Why too high?
But 1 and 2 is the most suggested one.
Yes.
Huh?
1 and 2 is the most suggested one, right?
Yeah, but the higher the mesh, the higher the finer the mesh, the higher the accuracy.
Accuracy. It will take quite some time, yeah.
Only a few minutes.
Few minutes. Right?
Yeah, yeah.
Let's donate to a computer.
Later, if your computer cannot handle it, you can come back here and turn the accuracy down.
Let's see the maximum capacity.
Why the non-uniform mesh is using? Automatic is understood, but non-uniform.
Non-uniform is that in this circular area, it has a higher refractive index, so the mesh has to be finer. And this program, it will automatically refine the mesh in this area.
Yeah.
So that's the for the mesh. And then we go to boundary setting. I think yeah, here X minimum, X maximum, Y minimum, Y maximum. They are all PML. PML is short for perfect meshed absorption layer. So we keep it as default. But if you use it in the future, you might need to define other boundary conditions. But that's another topic. We can keep it as PML for now. Let's see. We have defined the boundary. We have defined the mesh, size, general. Everything's fine. We can click OK. Again, we can click this zoom extend. Yeah, zoom extend to make the display a bit nicer. We have our simulation region. We have our structure. Next thing is to define the source.
Total field, scatter field.
Yes, total source, total field, scatter field. Same thing. Right click. Yeah, edit object.
Okay.
Here there are a few settings we need to do. First, on the first, let's give it a name. Source 1.
Okay.
On the general tab, the injection axis, let's set x-axis.
Oh, injection for the light.
Yeah. Directions forward, amplitude 1. This all keep as default. The polarization angle we change it to 90.
Okay.
This polarization angle is the angle of the electric field. So we want it to be perpendicular to our simulation plane. So let's set it to 90. So everything's fine. Then let's move to this general to define the size. The size 0505 00. Because we're working in 2D, so 0 span can be 0. Therefore, Z span can be 0. This is the size 5 by 5. Then let's go to this frequency / wavelength. So this defines the wavelength span we want to simulate. Because for example, if you are only interested in the UV range, you need to launch a source that spans the that covers the UV range. If you are interested in infrared, you want a source that covers the infrared. So here's the here's
we have
where
it
we
in
can do
visible
that.
range.
Yeah. Here's where we set the range. Wavelength start. Let's put 1 micrometer. Wavelength ends. Let's put 2 micrometer. So the simulation is from 1 micrometer to 2 micrometer.
Also infrared range.
Yeah. So everything else we keep it same. Yeah. Default.
What's the time domain? Is it a Fourier transform from the wavelength?
Yes. Yes. But this is automatic. We don't need to set it.
It's according to the wavelengths, right?
Yes.
Okay.
It's the inverse Fourier transform of the wavelength. Everybody got it?
Yes.
Same page?
What's the dimension?
Then we click
That's the
OK.
dimension, the radius we have mentioned.
In the circle, you can see that.
Now the screen should look something like this. We have this big yellow box. This is our simulation region, and we have like this gray box. This is our source. We also have a pink arrow. This indicates the direction of the injection. And finally, we have this circular objects. The next thing we need to do is
See the waves, they have a different height, radius of the cylinder, square.
I think it's just the display because I'm using a newer version. The blue, the important thing is that you have blue arrow pointing upwards.
Yeah.
Yeah. Me too.
Yeah. The depending on your file on your software version, it might looks a little bit different than mine. I think for yours you have also have a blue arrow pointing upwards in this view, right?
No, the green one.
Yeah, green one.
Blue arrow is in the cylinder.
Yeah. So now you have a green arrow pointing downwards in this view. Yeah. It's okay. It's just a display. The green arrow represents the magnetic field.
Oh.
The blue arrow represents the electric field. The important thing is that we have this blue arrow pointing up.
Sure, we do have it.
It should be perpendicular to the cylinder.
Yeah.
Z direction.
Yes. Our simulation plane is like this. It cuts through our cylinder.
The pink is the source. Yeah, they have defined 90 degree perpendicular to the source, electric field.
Yeah.
So it comes blue.
Yeah. So everybody getting the same?
Yeah.
Finish? Okay. Next, we are going to define some monitors because we have a source to excite the cylinder. Next, we put some monitors to view the simulated results. First thing, let's create a movie results, a movie monitor. We go here, monitor, and click on the inverted triangle. And here, there's a movie. This will show how the fields evolves with time. Click the movie and yes, edit. The first, let's give it a name. Movie, yeah.
Maybe a solar movie.
For this, for general tab, we keep everything default. Yeah. For geometry, let's first we need to set the monitor type. Right now, it's the correct one. It's 2D Z normal. It's it's 2D Z normal. Then
Why is Z normal, not XO normal?
Because our simulation is in this Z plane.
Okay.
Right?
XY.
Yeah, XY plane. Yeah. It's in XY plane, so Z normal will cover the whole simulation area.
XY plane.
XY plane.
Yeah. And then let's set the size of the. This will define the region of the field we want to record. So we put it 10 by 10 to cover the whole simulation area. I think that's all we need to do. For advanced, we leave everything to the default value, and then we click OK. Now the screen looks like this. There's another big yellow box covering the whole simulation area. That's our movie monitor.
Okay. It will measure the scattering light.
Huh?
It will measure the scattering light.
Yeah, it will. Yes, it will measure everything in our simulation area, both the scattering and also
all the properties.
Yeah. Next, let's create another. Yeah, let's create a frequency monitor. The movie monitor will make a movie of the time evolution, but if we want to know the field distribution in the frequency domain, then we need to add this. This frequency domain field and power monitor.
Okay, and power. Okay.
Yeah. This will record the field in the frequency domain. We click it and same edit objects.
Change the name, frequency.
First, let's give it a name. This one. First, let's give it a name. Let's call it field power, field monitor. Simulation type to 2D normal. And then geometry. Here we need to define a monitor type. Right now it's the linear X. We need to change it to 2D Z normal. Then we go on to define the size. 4.4 by 4.4.
Okay.
Everything else we keep it to the default. We just need to set the geometry and the 2DZ normal. It's very easy, very convenient. Also the name. Let's give it the new name called field monitor.
Okay.
After this step, we can see there's an extra yellow box within our this gray box. Yeah. So this field monitor will record everything. Will record the total fields, everything, including scatters and the incident field.
The field monitor is inside the source.
Yeah, it's inside the source.
And you place two monitors, first for the time domain.
Yeah.
And second for the frequency domain. But for the time domain you put outside.
Yeah.
And for the frequency you put inside.
Only inside. Yeah.
Why?
It's just a choice, just a matter of choice. You can specify the size as any size as any value you want. For me, I want to make a movie of the whole simulation. Okay. So I put a very big monitor, a circuit, around our simulation area, and I'm only interested in the field in this area, so I put the field monitor here. You can put this monitor at the area of interest. Next, I will show how to add a point monitor. So if you are interested here, all our previous monitors are 2D monitors that monitors the a surface. If you want to monitor a point, then we can also do that. Go to monitor. This field time, it has this clock icon. Click, then we edit. First, let's give it a name, corner, because we will put it in a corner. Then general, we leave everything to the default, and the geometry, we can see the monitor type is point. Then we just need to specify the location.
Okay.
X 3.5, Y 3.5. And after that, we just need to click OK. We can see there's a
point around the
at the right-hand corner. There's a point. So this is a point monitor that it will record the field evolution at that particular point.
So we can define many point monitors.
Yeah.
As per a requirement.
Yes.
Okay.
For example, if when you simulate a plasmonic structure, you want to know the enhancement at a local point, you can add a point monitor there and get the field. Okay. The next few steps are very critical because we will define the monitors to simulate the scattering cross section. We go here, analysis. These are pre-built analysis components. This includes both the monitors and the code. We don't need to do. We can use it directly. So we go to analysis and choose this optical power. We can see nothing happens much, but the change is here. You see,
in the object library.
In the object library.
Okay.
You need to adjust the window size a little bit to be able to see it.
You can see. We can see. No problem.
There's this scroll bar. You can use it.
We want optical power.
Yeah. If see, you can. If you cannot see much, you can like this drag this window larger and scroll down. Find this cross section.
Cross section. Yes. Okay.
And then insert.
Yeah, and then insert.
It's at the center.
Yeah, it's at the bottom. You need to scroll a little bit. Click insert. And then at the object tree, you can see this cross section object. Everybody got it?
Yeah.
Okay. So now we minimize this window again. And right click on the cross section. Edit. Let's give it a name, total, because it will record the total field. And then this setup variable, the origin 0, 0, 0.